Adiabatic wind. The normal airflow over the Rocky Mountains is west to east. The air loses much of its moisture content and is chilled as it climbs the western side of the mountain. When it descends on the eastern side, the increase in pressure lowers the altitude and causes the temperature to increase. The flow, then called the Chinook wind, can rapidly raise the air temperature at the base of the mountains. Assume that the air pressure P depends on the altitude y according to this equation. P equals px e to the negative ay, where P is 1 atmosphere and A is that number per meter. Also assume that the ratio of molar specific heats is gamma, 4/3. A parcel of air with an initial temperature of -5 degrees C descends adiabatically from initial altitude of 4267 meters to final altitude of 1567 meters. What's its temperature at the end of the descent? So we have an adiabatic process happening here. So there's four types of processes in thermodynamics, right? There's constant temperature, constant pressure, constant volume. Those are all exactly what they sound like. The quantities, temperature, pressure, and volume are held constant, each of those. And then there's one more, the fourth process is adiabatic. And in an adiabatic process, the temperature is changing with no exchange of heat. So this is kind of a special case compared to the other three. The quantity that's held constant for adiabatic is not any of the basic ones, temperature, pressure, or volume. Rather, there's actually two of them. It's PV to the gamma, where gamma is the ratio of specific heats, and TV to the gamma minus 1. So let's just hold on to that thought for a minute. We're going to relate those, but let's take a look at the information they've given us first and foremost. We have a wind going over the mountain. We know that the formula for the pressure is given by this function that depends on the altitude and the initial pressure, which is atmospheric pressure, and this constant A, which we've been given. And we've also been given the altitudes at these two states, y1 and y2. So let's write this down. We have this formula, P equals P0 e to the negative AY. And we know y1, we've been given that initial altitude, it's 4267. And we know y2, that's just another altitude after the fact. Final altitude 1567. I'm not sure why these are meters. They didn't give us a subscript 2 here, but we can certainly use one. And we can find the pressures from these altitudes. So let's grab the calculator and just do that before we really even get started. So we have some raw numbers to go on. So P0 is 1 atmosphere, so I'm just going to do 1 times, obviously it's itself, e to the negative A, so negative 1.16 times 10 to the negative 4, and that's times the altitude, which is 4267. 4267. And we get 0.6096. So P1 equals 0.6096, and that's atmospheres. We could change this to pascals, but I'm going to keep it in atmospheres because we're going to use it as a ratio. And then the second altitude, let's use second entry, so we cannot type that whole thing in again. The new altitude is 1567. Conveniently also ends in 67. 0.8338. P2, 0.8338 atmospheres. So we now know the pressures at state 1 and state 2. And the other thing that we've been given here is gamma. Oh, we know the temperature at one of the states too. We know T1. I'll put T1 up here. Is -5 degrees Celsius, but we never use Celsius temperatures in thermodynamics problems when we have to use ratios, right? We have to add 273 and put this in Kelvin, so that's 268 Kelvin. And then T2 is what we want. We want to know the temperature at the end of the descent. And we've also been given gamma, the ratio of specific heats, and that it's an adiabatic process. So we kind of alluded to that before. We cannot use the ideal gas law and just assume that T, and V change in a particular way where the moles are constant. We have to consider the fact this is an adiabatic process. So the quantities being held constant are PV to the gamma and TV to the gamma minus 1. So those are going to be the relationships we want to use. Unfortunately, this one gives us well, actually, let's spell this out a little more. What do these really mean? These mean that if you know the pressure and the volume in one state, and you know the pressure or the volume in the final state, you can find the parameter you don't know. For example, P1 V1 to the gamma equals P2 V2 to the gamma. So if you know any three of those, you can find the fourth. You can relate, and we can write that a little differently too. And the same with the temperature and volume. So if you have T1 V1 to the gamma minus 1 equals T2 V2 to the gamma minus 1. If you have any three of those, you can find the fourth. But what do we have? We have two pressures and one temperature. So we really want an equation that allows us to relate pressure and temperature. We don't have one. We have something that relates pressure and volume, and something that relates temperature and volume. So we could do this as a two-step process. We could use the pressure ratio to give us a volume ratio, and then use that volume ratio to give us the temperature ratio. But I'm going to propose we do some of that algebra on the front end and just derive a formula that gives us temperatures directly from pressures. So what I propose is that we solve for the ratio of the volumes and use that as a go-between to relate the pressures and the temperatures. I know that sounds like a bit much, but it's not nearly as bad as it sounds, I promise. So we've already written these in terms of states 1 and 2, just the way we have here. So I propose to solve for V1 divided by V2. So let's divide by V2 to the gamma on the left side and divide by P1 on the right side. So we'll get V1 over V2 all to the gamma equals P2 over P1. And then we want to get V1 over V2 by itself. V1 over V2 by itself. So we raise both sides to the 1 over gamma. The left side becomes gamma times 1 over gamma, which is just 1. And the right side becomes P2 over P1 to the 1 over gamma. Okay, so we got V1 over V2 by itself. Let's do something similar here. We'll divide by V2 to the gamma minus 1 on the left side, so that we get V1 over V2 to the gamma minus 1. And we'll divide by T1 on the right side, so T2 over T1. And now we want to get V1 over V2 by itself, so we will raise both sides to the 1 over gamma minus 1. So T2 over T1 to the 1 over gamma minus 1. And now we can relate these two, because V1 over V2 must equal V1 over V2. So we can relate this pressure expression to this temperature expression directly. So let's do that. And I'm going to write the temperatures on the left. So T2 over T1 all to the 1 over gamma minus 1 equals P2 over P1 all to the 1 over gamma. Now how do we get T2 over T1 by itself? We have to raise both sides to the gamma minus 1. T2 over T1 raised to the gamma minus 1, so this is going to go away. And the left side will become raised to the gamma minus 1. So P2 over P1 raised to the gamma minus 1 over gamma still. And now we have an expression that relates temperature and pressure directly. So if we want to solve for T2, all we got to do is multiply by T1 on both sides. So let's come up here. T2 now equals T1 times P2 over P1 all to the gamma minus 1 over gamma. And I'm running out of space, so I'm going to erase some stuff at the top. If you need it, you can run the video back. And let's come right to the top. And let's plug in our numbers, right? We have T1, P2, P1. We know all those things, and we know gamma is 4/3. So T2 is going to equal T1 in Kelvin. Can't say it enough. 268 kelvins. times the ratio of the pressures, which is P2, 0.8338 divided by 0.6069, all to the 4/3, sorry if that's a little messy, 4/3 minus 1 all over 4/3, and this is all in the exponent, so just wanted to write it big enough to see it. Let's grab the calculator and plug those numbers in. Let's see what we get. We have, let's do the exponent first just to see what that is. We have 4/3, which is that result. Subtract 1 from that, and then divide by the quantity 4/3. 4/3. We get a quarter. Right? Let's just sense check that. 1/3 divided by 4. Yeah, that makes perfect sense, right? Because let's just go up here for a minute. We really didn't need a calculator to do that. 4/3 minus 1 is 1/3 divided by 4/3. 3 cancels, and you end up with a quarter. Right? So that's consistent with our calculators telling us. 0.8338 now divided by 0.6069 gives us this ratio, and that's being raised to the 1/4. Raise that to the 0.25, and then that whole thing's being multiplied by 268 degrees Kelvin, and we get 290 Kelvin. T2 equals 290 Kelvin. And you can subtract 273 from that if you want to get it in Celsius. You will get 17 degrees C, I believe. See if that's the answer. Yeah, I got 16.8, close enough. So that's basically an adiabatic process with a bit of algebra there, but the big clues were adiabatic and gamma being given. That's what brought us to the realization that we had to in some way be using PV to the gamma and TV to the gamma minus 1. So if you take one thing from this problem, let it be that those quantities are constant for adiabatic processes.